Okay, let's pick up where we left off. We're talking about proteins, right? And so we are looking at the R groups. So we left off talking a little bit about the basic structure of the monomers to basically build proteins from, right? So you build your proteins from amino acids. That's basically what they are, just long chains of amino acids. And we left off, remember, talking about how amino acids are largely all, for the most part, the same, right? In the sense that they all have the same basic parts to it. They have the amino group, they have the carboxylic acid group, they have the central carbon with a hydrogen on it. So all this down here below the R is the same. The only thing that varies from one amino acid to the next is the side chains, of which there's 20 to choose from. And so when you take a look then at these side chains, these R groups, this is what basically creates the chemical personality. So a given amino acid will have its chemical personality given to it by the R groups. Now, obviously the amino groups and the acid groups, they also have some sort of play in there. Obviously there's like an acidic type of a presence with the acid. There's a basic type of presence with the amino group, right? Think ammonia, right? Ammonia is very basic in nature. But aside from that, all of them have that, right? So all of them have that kind of duality, that kind of base acid kind of bipolar personality sort of situation going on. What really makes them all stand out is their R groups. Now, when you take a look at the R groups, you can actually classify them into specific categories of function. So the first group that we run into are the non-polars. And so these guys basically are going to be hydrophobic, as is the case with all non-polars. And leucine is an example. You don't have to necessarily memorize that leucine is a non-polar, but that's just an example of a non-polar. Other side chains are polar, but they're uncharged. So what does that mean? That basically means, first of all, they're hydrophilic, right? So they're part of the water lovers. So remember when we talked about the tension between the hydrophilics and the hydrophobics, how much they hated each other, right? So you're already setting up some interesting characteristics associated with these amino acids already, just by the sheer fact that the hydrophobics and the hydrophilics hate each other. Okay, so you're already starting to set up some tensional dynamics there. So when you're looking at polarity, right? So first of all, like when you look at nonpolar versus polar, remember we talked a little bit about in the beginning of the chapter, how that generally speaking, if you see a molecule that is rich in carbons and hydrogens, you're probably looking at a nonpolar molecule, right? So you'd expect these R groups to have mostly carbons and hydrogens in this R group of varying structures and arrangements, okay? Now, in a polar, remember what makes a molecule polar is the hydrogen bond, right? The ability to kind of form a hydrogen bond, and that's due to the difference in electronegativities between atoms, right? For instance, oxygen being high electronegativity, sucking all the electron cloud toward itself, making the oxygens appear in practice to have a slightly negative-ish characteristic to it, right? Because it's sucking all those electrons toward it. And then the nitrogens, on the other hand, the things that are attached to nitrogen, then we looked at like hydrogens, which tend to be very weak in electronegativity, tend to pick up a positive charge, right? So you're kind of have these positive negative interactions setting up just the same way we saw when we looked at the properties of water, right? As being driven by that polarity of water. So the exact same things are happening here. So what does that mean then? So what that means is, even if you don't have any clue whatsoever what the amino acid is, then if it's a polar uncharged member, you would expect to probably see some sort of oxygen presence in the R group, because that's what would create the polarity, right? So you'd have some hugely electronegative atom in there, usually either an oxygen. And the other big one was what? You remember what the basis of the hydrogen bond was? Electrostatic interaction between the positive hydrogens of one molecule and the what? There's three of them. Oxygen's one of them, right? Fluorine was another one, but we don't have that in biology, right? That's a chemistry one. What's the third one? Nitrogen, right? So then you would expect that in a polar side chain to see some sort of presence of either oxygens or nitrogens, right? Because both of these are heavily electronegative, and these would create that imbalance in the electron cloud, creating polarity, right? So you'd expect to see those in there. Even if you don't know what it is, you can kind of take a look at the R chain and be like, you know, you've got an oxygen in there. I think you're probably polar, right? So you can kind of hypothesize, if you will, and kind of figure out that some things are polar or not without even knowing anything, right? This is kind of the reason why we go through this, because sometimes you're going to be hit with molecules and you can kind of reason your way through it if you just know a couple of basic principles, okay? Which is the reason why we stress these basic principles, is because that'll give you the tools you need to sort of think your way out of a jam. So we also have another group of hydrophilics, the charged ones. And so when you're a charged species, generally speaking, you're going to be picking up either a negative charge on the oxygen, or what you'll see is like an amino group that has a positive charge. So this basically would be acidic, and this one would be basic. So sometimes you see, instead of positive and negative charge, what you see is as acidic amino acids and basic amino acids. And we'll take a look at a couple of these here in just a second. But these are also hydrophilic, right? Obviously much more aggressively hydrophilic because they're actually charged. So I mean, a non-polar is gonna be like, whoa, wait, no, you know, get away from me, right? If I had a problem with water, I have a serious problem with you, right? Because you're walking around all sort of like staticky and that kind of thing. You can also put amino acids, there's a group of them that you can put into what's called an aromatic group. So an aromatic is an organic chemistry usage of that term. So it's not aromatic that we think of, like aromatherapy, right? So it's not like a good smell. Aromatic is actually the term that organic chemists give to any molecule that contains that benzene ring. So remember, we saw that when we looked at the functional groups. I kind of put an example up there of that benzene ring. And any molecule that has that benzene ring, by the way, the benzene ring is a really interesting molecule in organic chemistry and OChem 2. It's got like a couple of chapters dedicated to it. So there's an entire family of chemistry that goes with this benzene molecule. It's very unique. It's super stable. And it has like a lot of, like, there's a lot that it does. And so that's the reason why it gets its own functional group family called the aromatics. And what we mean by aromatic in this case is any kind of a ring-like thing. We kind of bend the rule a little bit with the amino acids, right? But any kind of a ring-like structure, if your R group has any kind of a ring-like structure that has alternating double bonds in it, then we kind of toss you into that sort of aromatic-ish type of grouping. Okay, obviously benzene is sort of the standard of that sort of ring-like structure with alternating double bonds. Phenylalanine is a good example of that one. And then you have the outliers. So those that kind of defy categorization, they kind of have special features in their own right, and each one has a slightly unique sort of a feature to them. And we'll take a look at that here in just a second. So those are the major kind of personality categories that you can put yourself in. If you think, if anybody's ever done like a Myers-Briggs kind of a temperament assessment or something like that, and there's lots of them out there. It's not just Myers-Briggs. I mean, there's all sorts of them out there. Some of them do they categorize you like dogs, right? Right? Like, you know, some people are golden retrievers and other people are chihuahuas, whatever that means, right? But they have all these different things. They talk about the temperament of the person, right? That's just kind of how you're hardwired. This is kind of like the temperament of the amino acid. Okay, so it's around this then. Now, the reason why this is important is because when we go to build a protein, this is what we're working with. Imagine that you're in control of building a team. I give you a project. It's a super, super critical project. And you're the one who's in charge. It's up to you to now build your team who's going to solve this project. Think of it kind of like the Broncos are doing it right now, right? So they just basically handed the keys to the Ferrari to Sean Payton. Now it's up to him to assemble his staff, right? So he's got to go out and look for all of the coordinators and the assistant coaches, and he's got to build his staff, but it's on him to do that, right? So the question that you always have in mind is, who do I have to pick from, right? What kinds of personalities do I have to choose from, right? Are they all just like bubbly, expressive people? I mean, that's going to be a really high energy group. They may not get a whole lot done, right? Or are they like just really just, just bottom line driven? It's like, listen, cut the crap, get to work, right? I mean, that's going to be a hard group. I mean, those are going to be hard people to work with, right? Because they're going to be just straight to cut to the quick. It could also be a good group to work with, right? So you can see that there's temperaments. As you're building this is kind of what you have to sort of work with. So how are you going to build your group? Are you going to have a mixture of all of them? Are you going to go all hardcore? Are you going to go all happy, bubbly, like Nathaniel Hackett, for all you Broncos fans, right? Or is there something else that you're going to do? This is what you have to choose from, right? So these are the types of personalities that you have to choose from in order to build your protein. Now let's take a look at it in the scary version. Okay. Now, normally speaking, whenever you first see this particular image, most students stop breathing for a second or two, and that's normal. Just keep breathing, deep, in, out, in, out. So I don't put this up there to scare you necessarily, but just to kind of organize you, to kind of draw a little bit more nuance to the previous list. First thing, one thing I will never ask you to do is, from memory, draw me the structure of phenylalanine. I'm not going to do that. Yeah, you're like, okay. There's one more breath, right? You're able to take a little bit easier. I'm not even going to necessarily ask you, okay, phenylalanine, what kind of a chemical category is it in? Aromatic, nonpolar, because I would require you to know the structure of phenylalanine. Like, to do that from memory, I would never do that. Okay, that's more like a biochem level of study, and this is not biochem. And I know that because I took biochem, suffered through biochem. I loved it and hated it at the same time. It's one of those sort of confusing classes where you kind of want to strangle everybody and hug everybody at the same time. It's a very confusing class. But anyway, that's the reason why I'm not a biochemist, why I'm more of a molecular biologist, which is a softer version of biochem. Right? But we do this to organize this, to sort of show you what we have to choose from. It's your task to build a protein. So how are you going to build it? Well, the first thing you probably want to know is, okay, that's fine, I can build a protein, but what do I have to build with? Right? You're going to want to know your materials. Just like if you were a mason, I said, your task is to build a brick wall. Great. The first thing you want to know is, what kind of bricks do I have? Right? Do I have the traditional red ones that we think about? Are they, different colors? Are they different sizes, different shapes? Right? What are we talking about here? Right? What are my monomers that I have to build with? Because that's going to dictate what your polymer looks like. Okay. And that's what we're talking about here. We're doing kind of like a study of, this is what you have available to you to build proteins with. Okay. And it helps to understand that, really, especially also to understand how proteins behave once you get to that point. So let's take a look at it. So first of all, in the columns, you're going to see we're going to be breaking these guys down by their polarity. So you can see in the first column, in the green column, are all the non-polar amino acids. Now you can see that they're non-polar. Why? Because if you take a look at the R chains, notice what's common to all of them. Carbon hydrogen, right? They're almost all carbon hydrogen, right? And we said that if you have a carbon hydrogen, a lot of them, you're probably non-polar, right? Now, also here you can see you have a benzene ring, that's carbon hydrogen. This is mostly carbon hydrogen, even though you got that little nitrogen in there, there's mostly carbon hydrogen in there. These guys are mostly carbon hydrogen, so you can see that. This is mostly carbon hydrogen, even though you kind of have a little bit of a funny business going on there with the sulfur. And if you see, sulfur is actually in the same family as oxygen, so it has similar chemical properties to it. But you can see it's mostly non-polar, largely because sulfur is kind of symmetrically oriented around nonpolar carbon-hydrogen chains, right? So you don't get that lopsided effect, right? The same thing we saw when we looked at methane. Remember, we said that methane has polar bonds in it, but it's a nonpolar molecule because of its symmetry. This is a similar sort of a situation. Because of the way that the sulfur is arranged, surrounded by carbon hydrogens, it doesn't have the capacity to be lopsided. That makes sense? So these are all nonpolars. And you can see they all have basically carbon hydrogen bonds to them, but they're also what we refer to as aromatic or not aromatic or something else, right? So for instance, the aromatics, I'm going to start off with these guys, are basically going in this row. So if you notice, the aromatics will have some sort of a ring structure in them, and usually we'll have these alternating double bonds. That's what you're looking for in an aromatic. But because these guys right here, the rings that they have are mostly carbon hydrogen, it puts them in the aromatic nonpolar group. Okay, so you kind of like connect this side, so it's aromatic, connect this side, it's nonpolar. So that creates basically this sort of aromatic nonpolar. And then these guys don't have a ring. They're just basic chains, right? And so these guys would be the non-aromatics or the non-ring containing versions of the nonpolar molecules. And of course, these guys are just different, right? So like for instance, proline has a ring, but it doesn't have any double bonds in it. So it's not aromatic. And then of course, methionine has, mostly carbon hydrogens, but it's got this weird sulfur in there. So it's not part of the non-aromatic area, right? Because it's got this little weird sulfur that kind of throws a wrench in things. So it's kind of its own thing. Now, in the next column down, you have your polar uncharged. And remember, we said that if you're polar, you're likely going to have either oxygen, electronegative, or nitrogen, right, electronegative, or perhaps both, right? So when you take a look at the side chains here, you can see you got an oxygen there, got an oxygen there, got both of them there, got both of them there, right? So that gives you this potential to be very polar in nature. In terms, and none of that, but they don't have a ring, right? So they're just basic chains. So that makes them non-aromatic in nature. They're non-ring-like. This guy down here, tyrosine, has an oxygen on it and a ring, which makes it polar and aromatic because it's got that alternating double bond ring situation going on there. And then of course your outlier for this one, which would be polar, but not aromatic and not really normal non-aromatic. So this would be cysteine. You notice you've got a sulfhydryl group on there, which is related to the hydroxyl group. The only difference is you swapped out an oxygen for a sulfur. So the same kinds of polarizing properties that a hydroxyl group would have, like for instance, this guy up here, you also have in sulfur. So the sulfhydryl is kind of like a sulfur version of the hydroxyl. So really, if you think about it, cysteine and serine are kind of like siblings to each other in the sense that they're basically the same R group. The only difference is you swap out an oxygen for a sulfur. And because of the nature of the way the periodic table is arranged, as you go down a column on the periodic table, oxygen, sulfur, selenium, beryllium, polonium, things like that, Las Vegasium, whatever that LV is, Latvium or something like that. Or Latvia, that's actually a country, but I don't know. Right, so it sounded better than Las Vegasium, but anyway, right, so all of those, because they're in the same family, have similar characteristics, just like siblings in a family have similarities to the way they act. So you can see that me and my brother are siblings because we have a lot of mannerisms and things like that that are very similar, right? Just like, but we're not the same, right? Just like oxygen and sulfur and selenium, they're all similar. They're all siblings in the same family. So chemically, they have a lot of similar patterns. As a matter of fact, we were able to predict, we can predict actually, it's one of the things you do in chemistry, is you can actually predict what another member of a family would do chemically by what the other members of the family do. Like for instance, if you know oxygen well and how it behaves in a particular reaction, you could predict that sulfur would do a similar sort of a situation. They would behave very similarly. And that's because they're all very related. So that's the reason why you get this sort of nuanced sort of similarity between cysteine and serine. So they're both polar. And then you get to your charged ones. So remember, in your charged ones, you're going to be finding some sort of an electronic charge on there. So here you can see a negative charge on oxygen. There's a negative charge on oxygen. There's a positive on nitrogen there. There's a positive on nitrogen there. So these guys tend to be the acids, and these guys are the base. These are basic. So if you have that positive charge in your nitrogens, that's your basic. So arginine and lysine. And then you have your aromatic. So you notice it's not quite a benzene ring, but you can see that you've got your alternating double bonds. So it is a ring with some alternating double bonds. So we toss that in the aromatic group, and that's histidine. Now, that's a lot of talking for a slide that I'm not emphasizing, which is kind of raising your eyebrows, right? So wait a minute, did you just lie to me a few minutes ago? Possibly. No, I didn't. No. The reason why I do that is so that you have a sense, and some of these amino acids, you're going to like, oh yeah, okay, I remember that one. And some of you are gonna remember, and some of them you're not. And that's fine. But the reason why we want to understand that is because what we want to do is we want to start putting a protein together. And in order to create the characteristics and the function of the proteins, and the fact that proteins are all different from each other, is going to be attributed ultimately to the amino acids that we select. Just like your work group that you're using to solve your whatever your big task is that I just gave you, what that group does and how it functions is going to be a function of who you select. Every group is like that, right? I mean, and you may see it actually in your classes, right? I mean, every class is the same way. Every class has a different personality, even the same class. Like you guys, I mean, I have you in the morning, and then I have my 2 o'clock class, same class, bio 1111, and I have to choose it. You guys are like night and day personality-wise. Why? Because your personality as a group is a function of your personality as an individual. The individuals are what decides that. Okay, and I could create a completely different personality group if I selected individuals from each section and created a separate group. So the same thing's true here, right? Because your function of your protein, and there's a lot of functions, right? We already looked at that, didn't we? Big laundry list of functions that a protein is doing. All of those functions are basically a result of these 20 amino acids and how you put them together in combination. So let's take a look at it here for a second. So first of all, what's going to happen is we're going to take 2 amino acids, and the first thing we're going to do is we're going to break the bond in the carboxylic acid, so that hydroxyl terminal piece on the carboxylic acid. And then you're going to break the bond here, the 2 hydrogens that are associated with the amino group. Now, as soon as I do that, I'm not happy anymore, am I? Right? Because I had my octet rule covered until you came in and broke my bonds. Of course, same thing we see before. Dehydration synthesis is what's underlying this. This is the exact same thing you're doing, dehydration synthesis. So in this particular case, now what's going to happen is the enzyme is going to be like, listen, you know, we've done this before. So, you know, hydrogen, oxygen, once you meet each other and you leave as water. So we're all happy now, yes? But the amino acids aren't happy, right? So then what the enzyme says, listen, acid carbon, why don't you form a bond with the amino nitrogen? And when you do that, we're going to call you a peptide bond. So remember, each one of the bonds that forms that links these monomers together has its own name. In carbohydrates, the bond that linked 2 monosaccharides together is called what? There's 3 different types. Yeah, right? The glycosidic bond is the one that held those guys together. When you come to amino acids, they're held together with the peptide bond. Okay. As a matter of fact, this peptide is actually the root term for a lot of things referring to proteins. Like if you ever look at peptidase, that pept in the beginning is part of protein. That's basically a protein designation, is what that's part of. Peptone, anything like that, peptidyl transferase, things like that. So there's a pept root at the beginning is referring to protein, pepto-bismo. That original root is it's referring to protein. Okay. And so those are different situations. So what I want to do though is I want to do more than just link together 2 amino acids, I want to do a little bit of a string, because what we're going to do once we now figured out how to link these guys together is we're going to go through the 4 levels of protein structure, because unlike carbohydrates, where linking the individual monosaccharides together is sufficient, in proteins, that's just the beginning. Okay, so you're not really all that close yet to getting a functional protein. So here's what I want to do. I am going to start with the amino group. There's my central carbon, which has a hydrogen on it. And let's make this one the R group. And there's my hydrogen right there. So there's my first R group. But this is going to be linked to my acid, which is because I'm linking them together by a peptide bond linked to the next amino acid. So this one will have a hydrogen here. My central carbon, I'll put the H up there. My next R group will be down here. Here's my next acid, which is still linked to another nitrogen. I'm still going to do this. My central carbon. Here's my third side chain. There's my H right there. Here's my acid. Let's do one more. Be like Bob Ross, happy little amino acids. For all you Bob Ross fans. All 2 of you. And then we'll terminate it. All right, so that's basically a tetrapeptide, and it keeps going. You just keep on going for as long as you want to go. But that's good enough for now. So you notice on one end of your chain, you have an amino group. We call this the N-terminus. In biochem speak a lot of times. And of course, on the other end, you got your carboxyl group, which we refer to as the C-terminus or the carboxyl terminus. Now, one thing I want to point your attention to is notice in the center, you've got a repeating unit, don't you? NCC, 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 and so forth. So this is what's referred to as the backbone. So when you pluck out the backbone and you identify the backbone, now what you can see are all these little pieces sticking out from the backbone, kind of like branches from the main trunk of a tree. Okay, some of those branches are the R groups. Some of those branches are associated with the backbone, right? Let's identify a couple of things. So we've already just talked about all the different categories of R group chemistry, right? And we don't know which R groups these are. So they could be any type of those 20 different chemistries, right? Non-polar, polar, charged, whatever, it could be aromatic or not. So we don't know what they are, but these R groups can be anything, right? So we know that those personalities are there. But let's take a look at the backbone a little more closely. And think in terms of electronegativity. So let's go, first of all, to this oxygen right here. This first oxygen for this carbonyl. What kind of electronic state does that oxygen have? Charge state, basically. Why? It is negative, yes, but why? Lucky guess. So if you take a look at it, right, this is a bond polarity, right? Because your bond is carbon and oxygen. So if you take a look at the periodic table, who's got more electronegativity? So oxygen is going to do what? It's going to suck all the electrons toward it, right? Making it have a more negative-ish personality. It's a polar bond, right? That's true for all the oxygens. Now let's take a look at the hydrogen on the nitrogen. So the nitrogen hydrogen, is that a polar bond? The nitrogen hydrogen bond? Ooh, poking the soft spots. Yes, exactly, right? So nitrogen is a lot more electronegative than hydrogen. The difference actually between nitrogen and hydrogen is stronger than the difference between carbon and oxygen. So what that means is hydrogen is going to have what charge state? Positive, right? And it's going to be more strongly positive probably than the oxygen is negative. And that's going to be true for all of these nitrogen hydrogens. Right, add these guys out here too. So now let's take a look at it. Now what you're seeing is not just the backbone, but now you've got the backbone with all these little positive and polar pieces out there sticking out of it. So you have the negative oxygens, the positive hydrogens, and that's before you even get to the R group discussion. So the reason why you want to keep track of that is because what can you do with a positive pole and a negative pole? Yeah, right, they can attract together in a hydrogen bond. And that's exactly what happens when we go through our 4 levels of folding in a protein. So the first level of folding is what's called primary structure, first degree. Literally, it is the sequence of amino acids. So what I just wrote on the previous slide is literally the primary structure of whatever that is. So it's a little tetrapeptide, right? So that's primary structure. But remember, the primary structure not only has the R group sticking out of it, but it's also got these polarized side pieces, you know, the negative oxygens and the positive nitrogens also sticking out from it. Now, the reason is I mentioned that is because that has consequences. Because as soon as you basically create that chain of amino acids, then you move into the next level of structure, which is the secondary structure, the second degree. Now, at this particular level, what's going to happen is you're going to start to see interactions between the backbone. The backbone oxygens start to form H bonds with the positive hydrogens. But this is backbone interaction. You haven't even gotten to the R groups yet. So let's take a look and see what that looks like with our little tetrapeptide friend. So what does that look like? Well, what that basically means then is, like, for instance, this hydrogen may see this oxygen over here and want to form a hydrogen bond with it. Maybe this hydrogen here sees this oxygen right there and wants to form a bond with it, a hydrogen bond with it. When you do that, what happens is you distort the backbone. So for instance, if you had a backbone like this, where you had a positive hydrogen over here and a negative oxygen over here, those two will want to come together to form a hydrogen bond. So what happens is you're going to fold the backbone so that you can create that create that hydrogen bond between the two of them. So what you've done is you distorted the backbone, you folded it up. Now this is happening with all the rest of them too. So the more of those guys are coming in close proximity, they're going to want to form hydrogen bonds with them, which further distorts and folds the backbone into basically kind of like this sort of folded up pattern. Now, because the backbone is continuous, right? So all amino acids, all proteins with an amino acid chain have the same repeating backbone, NCC, 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 which means they've got the exact same situation, right? Negative oxygens, positive hydrogens. So if you were to just take a look at the primary linear sequence of any given protein, then they would look very similar, right? Because there's no variation here at this point, right? This is what's in common with all proteins. So as a result, the consequences of that folding creates two very common patterns. That's true for all proteins, right? This is because they all share the same backbone structure. And there's those two patterns is the alpha helix. This is basically where your backbone will fold up into like a helical coil, and then it'll be held together with these hydrogen bonds. Or it'll form what's called a beta pleated sheet, where it kind of folds like a little sheet. and it's held together with hydrogen bonds. So that's secondary structure. And you see that in every single protein because they have a common backbone, that NCC, NCC, NCC repeating unit. However, where the proteins get different is in what you do next. And that moves us into tertiary or third degree folding. This is basically driven by the interactions between the R groups. What does that mean? That means you're going to get your nonpolar versus polar repulsion, your nonpolar versus nonpolar attractions, right? So all those interactions between all those guys, the hydrophilic, hydrophobic realities, those are all going to start to show up here. Why? Because what you've just done is you've used your backbone to fold yourself up. But what that's doing is that's bringing two different, oftentimes very far-reaching R groups that are far away from each other in a linear space. But when you fold that up, you bring those two into close proximity to each other. And if they are a polar and a non-polar R group, then they are going to flee from themselves, right? They're going to run away from each other. And that's going to further distort and bend the backbone, right? So the polar molecules will run toward each other. The non-polars will run toward each other and away from their enemies. All of that, through all the R groups, as that's going on, everybody's trying to situate themselves out, is further distorting the backbone and causing this structure to continue to fold even more. So what you see then in tertiary structure is this kind of globular protein effect, where you've got elements of secondary structure in there. So for instance, you might have a helix, and then a loop, and then a sheet, and then a helix, and then loop, and another helix maybe, and then here's some sheet, and then a helix, and then maybe a little lumps, and then a sheet, and then another sheet, and then a loop, and then a sheet, and then a helix, and then, it's kind of all over the place. So some sheets, some helix, and it just kind of gets all gummed up and wadded up into this large globular protein. Now, for single subunit enzymes, this is the end. You're done. You can go do your thing. But that's pretty rare, right? Every protein gets this far. Most proteins will wad up into some sort of a tertiary structure. Okay, they will get this far. However, many proteins, I would say most enzymes, even ones that we associate with just doing one chemical reaction, are actually not a single subunit. They're multiple subunits or multiple proteins that come together as a functional team. When you do that, when functionally you have to operate as a team with other subunits that are also folded up into tertiary level, we call it quaternary structure. So this is where you have multiple polypeptide chains or subunits in a single enzyme. Good example of this is hemoglobin, HP. Hemoglobin is a tetramer. Tetra, 4, mer things. Has 4 subunits. So it has 2 alpha globin subunits and 2 beta globin subunits. Each one of them individually is folded up into their tertiary level, but they're not functional by themselves. So for instance, if you were to isolate alpha globin, it will not function. Beta globin, it will not function. They have to come together in quaternary structure as a team of 4. That's when they become a functional complex. And this is probably more the rule than the exception. So most enzymes are part of a team, generally speaking. And so that would be your 4 levels of structure. So here's kind of the visual version of all of that. So here you can see you've got your repeating subunit, your backbone, with your oxygens and your nitrogens surrounding it. So here's a oxygen, there's a nitrogen. And so you can see these will start to form your backbone interaction. So this is your primary, and secondary, you get your backbone interactions. So here you can see your beta pleated sheet, how it's kind of sort of folded up accordion style. But then you can see the basis of your hydrogen bonds. So this is an oxygen. This little white one is a hydrogen. And so you can see this is going to be the slightly negative, and going to be slightly positive. So you can see that little H bond right in there. So that right there is your hydrogen bond. So you can see you're basically holding these two accordion sort of folded sections together with those hydrogen bonds. That's the beta pleated sheet. The alpha helix, same basic idea. So here's your hydrogen here, here's your oxygen here, and you can basically see you're basically forming these hydrogen bonds holding these two coils together. And for the most part, that's kind of standard secondary structure, either sheet or helix. That's usually what's inside your proteins themselves. Then, of course, if you sort of take a bunch of these and you wad it all up into tertiary structure, then you get your globular protein. So here you can see, here's some beta, alpha, beta. Here's an alpha helix, here's a beta sheet, here's an alpha helix. And so you kind of wad this all up into a big globule, and then this is your tertiary structure. And then if this is a subunit like the alpha globin that is only functional in its team, that's your quaternary structure. So here you can see this represents one tertiarily folded subunit in a tetramer where you have 4 different subunits. Every member of that is also folded up into tertiary structure, that globular tertiary structure. Okay. So let's talk patterns. So a motif, typically in molecular biology, is a commonly occurring secondary structure pattern. That is associated with function. So here's what happened. Here's a good example. Right. So back in the day, we studied enzymes. We studied a particular, not an enzyme, but a protein. And this a particular protein had the ability to bind to DNA, to actually make contact with DNA and to kind of grab onto DNA. So what we want to know is like, well, how do you do that? Right. So what mechanism do you use to be able to actually physically attach yourself to the DNA? So what we found was a motif, right? So let's say, for instance, and this, I'm just making this up, it's not necessarily the DNA binding motif, but let's say that in studying this DNA binding protein and this area where it bound to DNA, we noticed that there is a helix, loop, helix. And through research, we figured out that that's actually the point where it makes contact with the DNA. So there's something about that that allows it to actually physically tether itself to the DNA. And so what we found out by studying other DNA binding proteins is that other DNA binding proteins also had the same pattern, helix, loop, helix, right? And as we do research on those, we noticed that it's like, well, guess what? They're using this particular pattern to bind to the DNA too. So what we got was basically this pattern that is assigned to function. So when we look at an unknown protein, protein X, and we know nothing about it, we can take a look at it and say like, oh, hey, look, it looks like it has a helix, loop, helix pattern. That's a motif. And because we know well what helix, loop, helix does in other proteins, we can confidently hypothesize that this probably is a DNA binding protein, or at least one of its jobs is to bind to DNA. Okay. And so we can kind of predict functions. Matter of fact, that's what we do now when we look at proteomics, like genomics and things like that. Like we'll discover some sort of sequence or some sort of a gene. We don't even have to do wet chemistry, get into the lab. We can actually just take the sequence of it, plug it into our database, and we can actually predict what it would possibly do, because it's like, oh, well, we see in the sequence of the protein, the sequence that you would need to create a helix loop helix, suggesting that this is a DNA binding protein, among other things. So we can actually do a lot of just computer work in terms of predicting the functionality of proteins before we even have the protein itself in the lab. Okay. And a lot of our big databases, this is the reason why the Human Genome Project was so huge, is because once you actually sequence the human genome, then you have the sequence you need to sequence the proteins, right? And then once you sequence the proteins, you can do a lot of predictive evaluation of those proteins and get a good idea of what these proteins are doing before you even enter a lab. And so it tells you a lot of information. That's the reason why genomics and that whole genome project is so big, is because it gives us a lot of information. So those are like motifs, and we see commonly occurring patterns that are usually associated with particular functions. Those motifs tend to exist within a larger structure, which is called the domain. So for instance, the DNA binding domain, or the area of the protein that binds the DNA, oftentimes will contain the DNA binding motif. So the motifs are smaller, but they exist within the overall domain itself. That makes sense? And there may be a bunch of other stuff in there. It's not just like helix loop helix and that's the domain. There could be other stuff in there. I mean, there could be a bunch of beta sheet and a bunch of other loops and other helixes that are in there in different sort of combinations in that DNA binding domain. But in that DNA binding domain is your helix loop helix, which we know is necessary in order to be able to make attachments to DNA. So there's their motif plus other stuff in the DNA binding domain. So these are larger, but they also tend to be functional units within a protein. And I'm going to take a look at this here in just a second. So here's a couple of motifs. You don't have to know what these motifs are. Like if we were in biochem or molecular biology, we probably would have a whole laundry list of motifs, kind of the way we had with our functional groups, right? We had a whole laundry list of functional groups and we kind of some ideas there. We do the same thing in molecular biology, and we study the functions of them, right? So if you have this, a leucine zipper, then this is what it is, you know? And so you'd have a lot of that probably that you'd be studying. But these are some common motifs we run into: beta, alpha, beta. So you can see here's beta, going to alpha helix, going back into a beta sheet. The helix turn, helix or loop. This is, here's your alpha, here's your loop, and then here's your alpha. So that's a commonly occurring type of a scenario that typically is associated with function. But the domain idea, this is something that a lot of times will kind of confuse students until I kind of break it down. So here's like this is what we're looking at here is like one subunit, like just like before, right? We have the subunit of a tetramer, right? That's what we use as the example. But within this subunit, you have different domains. Now, let's take a look at the domains. Domain number one could be specifically functionally tasked with being the catalytic domain. So this is the domain that you do your chemistry with. This is your chemical reaction. So this is the one doing the job, right, of whatever chemistry is that this particular enzyme does. Domain number two, let's call this one the regulatory domain. Where you're an enzyme, you're doing some sort of a chemical reaction, but you don't want to just do that chemical reaction all the time, right? You need to do it at certain times for specific purposes to a certain degree or a certain amount, right? So producing a certain amount of stuff. All of those instructions are going to be coming to you from your regulatory domain. So your regulatory domain is the enzyme's sort of way of being able to take on instructions. So there are all regulators that are managing the situation, telling these enzymes, you know what, you need to turn on now turn off, right? You need to turn on now, but I want you to be very, very low activity. And then what I want you to do is I want you to grow over time, and then I want you to stop, right? So it has to be able to take all those instructions. It knows how to do its job, the chemical reaction, but now it needs all of those instructions in order to know when to do it, how much to do it, and those sorts of things, and when to turn off, right? Think of it sort of like a musician in an orchestra. Every musician in an orchestra is accomplished, right? There's no question that they can't play, that they can play their instrument. That's not even a question. right? But what they have to have is not just their ability, just their raw ability to play the instrument. That's like their catalytic domain. But they also have to have their regulatory domain, which means they have to be able to take instruction. So they have to be able to take instruction from the composer of the piece who's writing their part in there, right? And also from the conductor. So the combination of the two, the music is telling them when to play and when not to play. The conductor is telling them the nuances of it. I want you to be this loud. I want you to crescendo or diminuendo, right? So I want you to get a little louder. I want you to grow in life. Or like when you're doing this, I don't want you to do this like, staccato, like da, 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 right? I want you to do it more. I want you to soften it up, right? And then kind of like ease into it. Da, 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 like it's almost a heartbeat, right? Like a pulsing heartbeat. It's the conductor's doing that, right? So the musician has to be able to take that instruction and then be able to sort of produce the product. And that's kind of what the regulatory domain is like. And then of course, the third one, this is what's going to be called the oligomerization domain. This is how it attaches to its team. Because remember, this is a tetramer. This isn't a Lone Ranger. This is non-functional if it's on its own. So it has to be able to have a physical ability to not just locate its partners, but then to also link to them, right? So if you look at every tetramer, trimer, or any kind of a complex, there's always an attachment point, right? Where the proteins actually attach to each other to form the complex. Well, that attachment point is this oligomerization domain or this sort of associational domain, where that uses this to reach out to its teammates and says, you know what? My catalytic domain, ready to roll. My regulatory domain, ready to roll. But now what I need to do is I need to form bonds with my teammates. So I need to reach out and grab onto my team members. We're all going to grab onto each other. And then once we grab onto each other with this domain, and we're taking the instructions for our regulatory domain, then we can fire off our catalytic domain. That makes sense? So those are all different regions. This is just one protein, but they're all having to do these different things, right? Just like a well-trained musician. Okay. Chaperones. Everybody loves a good chaperone, right? Or not. Spent probably most of their high school career trying to ditch the chaperones, right? Okay, what does a chaperone do? Ruin the party? Yeah. It makes sure that the relatively irresponsible younger members of the group don't manage to kill themselves. Right. So, but they're a constant presence, yes. I mean, chaperones don't just drop you off at the party and take off, and then the next time they see you is when they're posting bail money. Right. A good chaperone, like a high school dance, something like that, they're like everywhere, aren't they? Principals, teachers, I mean, they're like all over the place. You can't get rid of them. You know how you know that? Because if you try to do something bad, they're like all over you like fuzz on a tennis ball. I mean, you cannot get rid of them. And not only that, but you're not like having fun because it's like you're still on school etiquette because the chaperones are there. They still expect you to follow the rules. I mean, why am I here then? Right? So it's like, what's the point? But so they're everywhere. So one of the things that chaperones do, these are a group of proteins. And I want to kind of explain a little bit historically of how we originally saw chaperones and how we now see chaperones because of our increase in knowledge and our understanding of what happened. So here's how we used to think about protein folding. Basically, a chaperone aids in the protein folding process. We used to think these guys were just the fixers. What does a fixer do? But the idea is a fixer's only needed when? Yeah. So generally speaking, if things are done well, the fixer is an underused person, right? By the way, this is kind of funny, right? Because every political leader in the world has a fixer. The president has a fixer. All presidents have a fixer, right? They're different. We call them different things, and they have different titles and different positions. But every president has a fixer, right? This is somebody who kind of manages crisis and chaos and sort of makes things the way the president wants them. And most presidents, most good presidents, actually, it's not obvious who the fixers are, because the idea is if you're fixing something, something's broken, and you don't want to, advertise that, right? Especially if you're interested in gearing up for re-election, right? I mean, the most immediately past president is probably the most glaring example of being very out there with his fixers. Trump was notorious for having an entire entourage of fixers, and they were slimy, underhanded fixers, fixing all sorts of problems in all sorts of ways. And it was fascinating because it was all very visible. that was the head scratching thing about the prior administration is there's all these things going on, and these fixers fixing lots of things, and he had lots of fixers doing all sorts of things, but you just scratching your head like, why in the world are you actually airing this? I mean, nobody in their right mind would just be all out there, like, with this is like, anyway, that's yeah, anyway. That's why I said most presidents are better than that. Like Obama had his fixtures, but he was very good at hiding them. Very good at hiding them. Of course, he had his big personality to help cover that up too. But everybody has fixers. The idea is you only need it when it's broken. And so here's how we used to think. We used to think that because, and this was an honest mistake, right? And this is one of the reasons why I always push that idea, like, in science, it's important to make sure that you have your scientific mind on straight, right? That regardless of your idea, that you're always remaining objective, because you never know when you're going to uncover something that's going to require you to sort of upend a previously cherished idea or a model, because you used to think, oh, I think that's the way it is. It's like, well, it didn't actually turn out to be that way. So you always have to be open to that. Here's a good example. And because it made a lot of good sense too, right? Because think about it. We originally thought that chaperones, what they did as fixers, was all they did was just come in and tweak protein folding. But we used to think that protein folding was spontaneous. That all we had to do is just basically make the chain, primary structure, right? Just select them. And then everything else is going to be magic. There it goes, right? Now, that seems kind of dumb now, because it's like, well, why would that happen? Well, think about it, though. There's good reason for it, because think about it. The attraction, right? We're talking about the secondary level, right? So the attraction between the positive hydrogens and the negative oxygens, does that require a lot of sweet talking to get that to happen? No, because that's natural. I mean, those attractions are natural, aren't they? So you can get that by just spontaneously allowing them to be in close proximity to each other, but those positives and negatives will find each other, right? They will basically start to kind of gravitate toward each other, and then that'll kind of fold and bend the backbone. So that makes sense, right? Well, why wouldn't that be spontaneous? Because that's a natural attraction. If we have a positive and negative, they're going to naturally come together spontaneously. So why wouldn't that occur spontaneously? So that made good sense. Not only that, but take a look at the R groups, the next level, tertiary. When we're folding this thing up into a globular whole, those R group interactions, are those spontaneous? A nonpolar next to a polar, what's going to happen? Are they going to just chum up together and kiss him? No, what's going to happen? They're going to repel, right? Now, do you have to sweet talk that one to get that to happen? No, that's spontaneous, right? That's the organizational power of water. By the way, if you're wondering, that's what the non-polar, polar organizational thing, that's what that question was on the exam. But anyway, darn it. And the whole class is saying darn it, because almost nobody got that one right. Some did. Right, but that's spontaneous, right? So when those polars come together, there's an attraction to them. That's spontaneous. You don't have to tell one water molecule to form hydrogen bonds with another, right? That's spontaneous. Polar to polar, polar to charge, that's spontaneous. Non-polars running away from polars, right? That's spontaneous. So all these interactions are spontaneous. So if that's happening at the tertiary level, then that would be spontaneously happening as well. And then basically you'd get this sort of folded up protein. So it made perfect sense. It's very logical and very reasonable. But it turned out to be wrong. Right. So it actually, and then what happened then is if something's happening spontaneously, then what we figured out was that, okay, maybe every now and then they kind of get it wrong. Right. So if it's happening spontaneously, most of the time it's working. But maybe every now and then it doesn't work out quite the right way, it doesn't bend in the right way. And so it kind of gets a little wonky, or it has a little bit of a problem kind of folding up. But by and large, we used to think that maybe 80–90% of the time it gets it right. It kind of folds itself up and then we're off to the races. And then that, 10–20%, maybe 20%, a little high, probably like 10–15%. That's what we thought. That needs a little bit of help. And so what happens? In comes the fixer, right? To fix a problem. And oftentimes, if you want to think of it in terms of politics, right? I mean, for the fixer, the job could be something as easy as just shredding documents, which a lot of administrations do. And apparently keeping classified documents at your house, which apparently all presidents do. Both the current president apparently and the former. My guess is Obama's probably got a few things as well. I mean, but that's kind of the fixer, right? So hide those documents, shred them. Nixon was great at that one. So that's easy. Others, rehabilitating your image, that's hard. So those are also fixers. But that one's a much harder thing to do because if you've turned yourself into a national ass, you will never probably get over the fact that you are a national ass. I would argue that that was nothing new. There are lots of national asses in the world. Every country has theirs, or many in some cases. But basically these guys come in, give it a little bit of a tweak, right? Kind of maybe undo it a little bit. And then if you undo it and just kind of let it go, the chances are it's not going to screw things up twice. Assuming everything is normal, that the sequence is good, that if you kind of give it a little bit of an unfold and then let it go again, then it's not going to refold the wrong way twice. Okay. So that's just because it's random, basically. It's not going to do that. So that's kind of what they thought. Was it just basically only fix stuff? But there's a problem. That turned out to be really wrong. How do we figure this out? Well, what we did is we said, well, okay, first of all, here's what we're going to do. We're going to create what's called a deficiency, which is basically a deletion. So we're going to delete the chaperone gene, right? That's what we're going to do. And then we're going to take a look and see what this looks like. So then that's kind of the way we do things a lot, right? We say basically, what is your job, protein X? Well, what I'm going to do is I'm going to mutate you. I'm going to take you out, and then I'm going to analyze your absence, right? So if you were the one holding it all together, then I should see a very catastrophic fail in function if you are the one holding it all together. If you were basically, expendable, then I should also see that as well. Okay. Basically, this is if I take you out of commission, then whatever job it was you're doing will not be getting done. And I can analyze that and I can basically draw a one-to-one correlation that this is your job then because you're not there to do it. That's exactly what we did. So here's what we expected to see. According to our original model, the spontaneous folding model, we expected that if you deleted chaperones, if you had a deficiency in the chaperones, that you might see a slight accumulation in misfolded protein because there's nobody there to fix you. But for the most part, you'd be maybe 80, 90% functional. So it would be maybe a slight problem, but we weren't expecting a huge problem because most of your proteins would be folding normally. That's not what we saw. What we saw was a catastrophic fail. And folding. And in specific, we followed this in one particularly problematic gene for a chloride channel, cystic fibrosis. So basically, cystic fibrosis is a gene, or the gene that under cystic fibrosis, that encodes a chloride channel. That is to say, it's a channel that allows chloride ions to pass through it into the cell. And in this particular case, what we saw was that there was a failure to fold. Now, normally what happens is we mutate the chloride channel gene and we get cystic fibrosis, right? Because you don't have a functional chloride channel. That's not what we saw this time. What we saw was your amino acid sequence was correct. What does that mean? That means there's no mutation here. You shouldn't have cystic fibrosis if that's the case, because your chloride channel should be, by sequence, perfectly functional, but it's not. Why? Because when we analyzed it, we noticed that there's a fundamental failure to fold the chloride channel protein correctly. So it wasn't in the information for the chloride channel where the failure was. It was in the folding part of the chloride channel to make it functional. That's where the failure happened. And that's not chloride channel's problem. That's not the cystic fibrosis gene's problem. That was fine. That was perfect. What it is, the chaperone's problem.
Maybe this is a dumb question, but the chaperone proteins help other proteins fold what helps them.
And this is one of those chicken and egg moments in evolution, that there's several of them, that generally speaking, the evolutionary model has no way around. There's a lot of theorizing and hypothesizing and chicken first, egg first, and nobody can make any heads or tails because it's almost always circular. But that goes back to the origin of proteins, right? So you have the same idea, right, in molecular evolution, where it's like, okay, so we have proteins, which obviously we need to do stuff, right? But where do the proteins come from? Well, we need DNA for the proteins, but where does the DNA come from, right? And then the idea is like, well, if you have DNA and you have the information, you need to make the protein, but you need a protein to make the protein, right? So the actual maker of the protein to make proteins is a protein itself. So, right, so you kind of get this, and there's about half dozen very commonly occurring in discussion of those sort of chicken and egg questions, and most evolutionary outputs have no way around that. Don't. We know that obviously it must have been, but we don't know how. I mean, if you need a protein to make a protein, you need a protein to fold a protein, and who's folding the protein that folds the proteins? There needs to be a preliminary protein folder, which starts to just move you back into more circularity. And then there's evolutionary, they don't really have a lot of good answers for that one. That is those chicken egg moments are one of the biggest soft spots in evolutionary modeling. And I mean, we've got ideas that we can kind of model around it, but there almost none of them are satisfactory because there's not an answer. We don't know. We don't know who the original folder of the chaperone was. My guess is probably where the current evolutionary model is that the chaperones themselves were spontaneously folded. But I mean, that kind of is a problem because it's like, well, we just sort of contradicted that. So there's an issue there, right? So there's a lot of those sort of hamstrung moments in evolutionary modeling. That's kind of fascinating, but it's kind of what deepens the mystery. And so, I mean, we don't know. We have ideas, we have hypotheses, but I mean, a lot of them will have problems with it. Like you say, it's contradictory to what we just actually proved, which is the reason why why a lot of times scientists don't like to be open-minded. They like their idea and they don't want anybody, regardless of the evidence, to tell them that it's different, right? Because it does create these moments where it's like, well, wait a minute. So if this isn't a thing anymore, and if I stay open-minded, then I have to accept this one. But then we get back to the chaperone problem, where it's like, who folded chaperone? And that gets us back to, so it really causes a lot of problems. It's a headache. Scientists don't like to be in a place where they don't know, right? I mean, they're used to being the smartest kid in the class. They're used to having to be the ones with all the answers. And fundamentally, a lot of these sort of chicken egg questions, the correct answer is, I don't know. I don't know. There's not enough information. So the only thing that differentiates one protein from another is the sequence of R groups. The amino acids that you basically select in your primary structure. That's the only thing that differs from one protein to another. Mm-hmm. And that makes them different chaperones, right? Because there's more than just a chaperone. Yeah. There's multiple groups of chaperones, and they're all different from each other. So this is kind of how it works. So here you have your misfolded protein, right? And so basically you have your chaperone. It's kind of a dual chamber situation. So you kind of have a bottom chamber as well. But you got your internal chamber. Your misfolded protein is going to enter into your chamber itself. You're going to spend a little bit of energy. So it's an energetic process. You're going to basically use some ATP. You're going to cap it. It's kind of like a mixer, right? You mix it up a drink, kind of cap it, shake it a little bit. And then what's going to happen is your chaperone is going to kind of bend and massage the backbone a little bit, kind of knead the dough a little bit, right? It's kind of like you're making bread. And then that'll kind of allow it to sort of reform and sort of refold itself. And then once it does that, it uncaps it, and then out comes your nicely folded protein. Now, and this is kind of like the point at which, because in one of the, like when we did the honors version of 1111, we would read a research paper, a couple of research papers actually, and it actually touched on this particular process, this idea like what happens if you aren't able to actually fold your proteins. And that's a big problem. That's a big problem, because what happens if you can't fold your proteins, then you basically get a bunch of misfolded proteins laying all over the place, and there's not a good way to process them. And that creates a crisis. And then that causes bad things to happen after that. Okay. So the misfolded protein, there's actually a thing called the misfolded protein response, which is designed to go after misfolded proteins. So it's a thing, right? Misfolded proteins is actually a thing. And there's an entire biological mechanistic response to it. But it's designed to get these proteins folded correctly. You spend a lot of energy as a cell on getting these proteins folded correctly. And if you don't, then it creates catastrophic consequences. And the reason why it's important is because for a protein, remember, shape is everything. So we're just looking at folding up a protein in its three-dimensional shape. But always remember the three-dimensional shape equals for a protein function. Okay. Just like for you, three-dimensional shape equals function. So if I were shaped differently, I would not be able to carry out the same functions. How do I know that? Cut my arms off. You just changed my shape. I wouldn't be able to write with my hands. So for me to be able to write with my hands, I need this shape in order to do that, right? To eliminate that shape would be to eliminate that function. So this is an example, that structure function theme we talked about in chapter 1. This is a perfect example of that. Proteins need that three-dimensional structure in order to give them their function. It's absolutely critical. Megan.
And so chaperone proteins fix like misfolding. Can they combat things like unfolding proteins like certain specific functions?
No, they're not so much that. They're focused, by the way, on just the folding thing. There's plenty of work to do there in terms of our own proteins. And it's not just, and this is it's a little bit, so what we actually understand about chaperones is a little bit misleading from the slides, because the slides are actually just a wee tad outdated. But not only do chaperones aren't just involved in misfolding, they certainly are. That's their shtick, right? I mean, they're the main ones there. But they're also involved in folding in general, right? So as it turns out, and this is the reason why it's such a catastrophic fail when we get a chaperone deficiency, is because most of this is not spontaneous. I mean, there's a lot of spontaneous aspects to it, but really chaperones are there like the entire way. So it's not like, oh, well, you're just misfolded, so now you come in, because that would be their role as a fixer, right? That would be a very marginal role, but really they're required to actually bring in the actual protein, the polypeptide, and then to help it fold it together, right? It's just like when you have like flour and water and stuff like that, right? It doesn't just become spontaneously, a piece of dough that's all chewy and gooey and kind of like elastic, right? You have to put some energy into that, right? You, as the kneader, are involved in every step of the way. So it goes from kind of like more of a granulated, disaggregated clump of stuff to you basically smashing it in there, working that into the dough, and then turning it into a cohesive, elastic lump of dough. That's kind of what chaperones are doing. So they're kind of more involved all the way along. So they're kind of nannying the process from the beginning to the end, right? Not just the fixers at the end. That makes sense? So what happens then if you unfold it, right? So denaturation basically is unfolding the protein. This is an example, a good example of the nature of the three-dimensionality necessity for protein function. Basically, denaturation, when you unfold a protein, you're essentially killing it. Okay, so that's a dead protein. And there's a couple of ways you can denature a protein. Now, these are extremes. And we're going to use these examples as extremes because that's what you're going to do to denature. However, if you're talking about an enzyme, you don't need to be so extreme with these same metrics. These same metrics at lesser extremes can still affect an enzyme, right? It just basically affects its function. So you don't have to kill an enzyme to turn it off. We learned about this, didn't we, in the last chapter? Remember we were talking about the buffer? That's pH, right? You didn't have to make the buffer, the enzyme inactive by killing it, just simply by knocking it out of its optimal pH range, right? So you could still, that's a good idea, by the way, because that's good to know, because you don't want to just kill everything to turn it all off, because then you got to have to like remake it all, right? It's much more economical, think high price of energy in the cell, right? It's much more economical to come up with a strategy to keep your enzymes alive so you don't have to keep making them again. That's expensive, right? And just have a way to turn them on and off. Well, that's exactly what these at lower levels of extremity do. You can knock your enzymes out of their optimum and eventually turn them off. And all you do is just change your circumstances. But what happens then if you kill it, though, at these extremes? Well, if you have extreme pH, you can kill an enzyme. You can unravel it, right? Here's a good example. Make cheese with lemon juice, right? What's the pH of lemon juice? You remember this from last? Yeah, well, it's like 2-ish, right? So down there with stomach acid, right? So here you have a pretty harsh acid, yes? But you can make cheese with lemon. Actually, some people do, right? Anybody make cheese before? Not a bunch of cheese makers here. Why? What? With vinegar? Same thing, right? So it's a slightly less harsh acid, right? So lemon juice would be a stronger acid. But yeah, you could do it with any kind of an acid. But basically, the way you make cheese is you obviously want to get milk, first of all, and not just like, 2% milk. You want to get stuff with the good stuff in it, right? So raw milk, preferably, because it's got all the milk fats and proteins in it, hasn't been defanged, so to speak, right? So it's got all that stuff in it. A whole milk, if you can, is another option that a lot of people will use. But basically, what you do to make cheese is very simple. All you do is have to curdle the milk. And generally speaking, when you make cheese, you do it one of two ways. Normally in industry, you use an enzyme called renin, which actually is a commercial grade. You can actually get renin from a lot of different cheesemaker outlets and things like that. So renin is actually an enzyme. It's actually an intestinal enzyme that you find in sheep. And what basically that does is that will just denature, unravel all the milk proteins and things like that. So, but a lot of people who are vegans don't like the animal origin of the renin. So sometimes they'll make like vegan cheese, essentially. That's kind of a misnomer, right? It's kind of oxymoron, right? Because if you're not a lacto-ovo person, you wouldn't be messing with cheese anyway. But anyway, we'll leave that for somebody else to figure out. Right. But the idea here is if you take your milk, you put lemon juice in it, the pH will actually unravel the milk proteins, and it'll basically, the three-dimensional will go from, tertiary to secondary to basically primary. So it'll just unravel completely, linearize. And then when it does that, it starts to cross-link with each other. So the different proteins start to get tangled up with each other. And as they get tangled up, they start to kind of capture the other milk solids, like the sugars and the fats in the milk as well. And it becomes just a big glob, a curdled glob, right? So that's the curds. And then in cheese, what you want to do is you want to basically separate the curds from the liquid, which is the whey. And then once you do that, you kind of like strain it, and you usually kind of collect it up with cheesecloth. Cheesecloth is actually used for cheese making. And then what you do is you kind of press it to sort of wring all the water out of it, get it good and dry. Different amounts of pressing will give you different moistures of your cheese, depending on what kind of cheese moisture you want. And then generally speaking, you'll like wash it with some sort of a brine, or like maybe a bacterial treatment or something like that if you want some aging, and you let it age. Okay, that's your cheese. But the first step is curdling the milk, and acid will curdle the milk for you. Okay. So temperature, same idea. High temperatures will basically denature proteins. So for instance, cooking an egg, right? If you crack an egg into a hot frying pan, what color is the egg white as it's coming out of the egg? It's kind of clear, right? So egg white, just like most mammals, mostly albumin, right? Our amniotic fluid is albumin, our blood plasma is albumin, so it's a ubiquitous type of an animal protein. That's the reason why we use albumin as our protein example in the biological molecules lab. But once you actually cook this thing in the frying pan, what does it look after you cook it? White and, well, yellow, yeah, for the yolk, right? Solid, right? Opaque. You can't see through it anymore, can you? Basically, that's heat, that's denaturing of the albumin, which also unravels, cross-links together, gets tangled up hopelessly, and then creates that insoluble mass. Okay. And then to a lesser extent, ionic concentrations, these got to be pretty nasty ionic concentrations. Probably we don't have access to these sort of things. I mean, generally speaking, these are pretty nasty ionic concentrations. Your body's pretty good at regulating ionic concentrations. But with extremely high or low ionic concentrations, you can also denature your proteins. Okay. And so you can see that our use of pH, temperature effects, and ionic concentration is a way to kill a protein at extremes. Remember, these are all extremes. At lesser degrees, all you do is just inactivate the enzyme, not kill it. Okay. So here's a good example. So if you take a look at protein, right? Because protein basically is largely just a sequence of amino acids. That's all it is. Let's fold it up. And that's your protein. So when you're denaturing it, all it does is just unfold. It's still a sequence of amino acids. And it'll get cross-linked together, get tangled up, right? It'll kind of create this little opaque mass. It's an egg. But here's my question to you. Is there any difference between, for you, as an organism that wants to eat this egg, perhaps, is there any difference between the tangled up, unfolded mass of protein versus the original state? Think about it. Can you eat the egg raw?
Yeah, I can do it.
So does it matter to your digestive system if it's raw versus cooked? Well, if you think so, not necessarily, because it's just the same thing, right? Still your same linear sequence of amino acids. That's all it is. It's just that when you cook it, it just unfolds and gets tangled up. When it's raw, it's still kind of folded up like albumin. So does your body care whether you cook it or not? Does your body care whether you cook meat or not? In terms of the proteins. Does it? Is there any difference between cooking meat and cooking an egg? Is there any difference between cooking a meat, cooking an egg, and cooking a vegetable? If all you're doing is unraveling the proteins, does your body care? So then why do we cook food? It's a cultural thing. I like this. All right. Why do we cook food? If your body doesn't care whether it's denatured or not, then why do we cook our food? What? Because you like the taste of it, right? So there's a deep psychological thing. Okay, but biologically, think about it. We're the only species on the planet that cooks our food. Every other animal on the planet eats their food raw. So, biologically speaking, if we're an animal on this planet, do we need to cook our food? Ooh, hard question, isn't it?
I mean, you should cook the food, but say when you should not consume raw meat.
Why? If your body doesn't care whether it's raw or denatured. Well, okay, why are you going to get sick? Ah, bingo. So when we're cooking, what are we denaturing? Or do we care about the meat? No, it's not the meat we're denaturing. What are we denaturing when we cook? The bacterial proteins. The only reason why we cook is to kill the potential harmful organisms that are in the food, not to alter or change the food at all, because we can eat the food raw. If we have perfectly clean meat, we can eat a steak raw. No problem. All it is protein. It's the same, cooked or not. But the reason why we cook it is to kill the bad guys, right? You cook food for the exact same reason that you boil your water when you go up to the mountains. If that water's clean, do you need to boil your water? No. If your food is clean, do you need to cook it? Nope. Doesn't matter what it is. It could be a big old thick juicy steak. Bloody old steak. If it's clean, you don't need to cook it. It's a little gross, I would argue, but but you don't need to cook it, right? Because a protein is a protein is a protein. Doesn't matter if it's denatured or not. So that's a little think about that. I mean, we have entire networks, an entire psychology, food psychology, that's all based on something we don't actually need to do. The only reason why we do it is to kill bad guys. So literally speaking, all those channels, Food Network and things like that, when you see them cooking, you should be like, you know, if you actually had as good a food supply as you say you do, highfalutin fancy chef, then you shouldn't be cooking at all, should you? If you are as good as you say you are, then you shouldn't be needing to cook at all, should you? Right? But the idea is like, listen, if you're as clean in your food sourcing as you claim to be, right, 5-star chef, then you shouldn't have to cook a single thing. You should be able to feed it to us raw. Yeah, so that's a little scary, right? Because there are bad things in beef. So I don't think I would go for that one. But I mean, I'm just saying, right? Like, if, you know, it's kind of like seeing cooking, somebody cooking something is like an admission that, oh, hey, there's a bunch of bad stuff in our food. Why? Because we wouldn't have to cook it if it weren't in there. So it's kind of like, you know, well, you have to boil your water. Why? Because there's a bunch of bad stuff in the water. If you had good water, clean water, you shouldn't have to boil it, right? So it's funny that we look at water that way, but we don't look at food that way. It's the exact same thing. Okay, so let's start with nucleic acids next time. How about that? By the way, for lab, we're going to be doing, because of obviously snow day, and I'm thankful that we're actually here on a Wednesday for once. We're going to be doing lab, so we'll be out of sync, right? So we're going to be doing lab 7, which is the osmosis diffusion lab. So that means your retrospective for quiz purposes will be the previous lab, 5, 6, right? The microscopic labs. And then for prospective, that's what we're doing today. It's going to be lab 7, the osmosis diffusion. Okay.